Welcome to lecture 4 of module 9. In module 9 we are discussing on radiation heat exchanger and radiation heat transfer. In this module 9 we have so far discussed in last 3 lectures about that introductory basic concepts on and the various rules or various laws, and also that safe factor, and also we have seen that how to find that heat exchange, radiation or heat exchange, and how to do the calculations. That is what we have seen for black bodies and non black bodies. Now, in this lecture we plan to have 2 aspects we are going to discuss. One is the radiation shield, and another one is the radiation with the associated with the gases. So, these are the 2 important aspects that we are going to cover up in this lecture, and by that way we will be finishing this radiation heat transfer module. Okay. So, now to start with we will discuss about the radiation shield. Now, point is that what is this radiation shield? A radiation shield is nothing but a barrier that is being added between 2 surfaces which are 2 or more surfaces maybe who are going or who are involved in radiation or heat exchange. So, this barrier which is being added, this barrier material usually is of low emissivity, and what it does actually, it reduces the radiational heat exchange between the 2 surfaces usually which are involved in radiation or heat exchange, and that means that the radiation shield is nothing but an additional resistance that is put into the system. So, if we just try to define it, it will be like that: it is a barrier of low emissivity placed between 2 say plates in order to reduce the radiation heat exchange between the plates. So, there are 2 plates, and we are just putting some barrier to reduce the heat exchange between the plates. Now, one thing we should understand, that radiation shield, they do not, or radiation shields do not add any energy or rather to the system, or remove or do not remove any energy from the system. Okay. So, it does not involve in any kind of such addition or removal of energy. So, what it does, they only imparts additional resistance to the transport. Okay. So, there is a heat transport. So, it is acting as a additional energy. Now, let us see that how it does work. So, for example, let us say the radiation shield between 2 parallel plates. let us say. So, the first case is there is one plate, these are the two parallel plates, and the second case between the two plates, this is a plate and there is a sealed material that is added, these two parallel plates. So, I will say that this is in this case say it is at T1 epsilon 1, T2 epsilon 2, here T1 epsilon 1, T2 epsilon 2, and this is radiation material can be at T3, and it has got basically 2 epsilons. So, if we see that in this case, as I was discussing, so this is the situation. So, when we are putting a radiation material, that means what is happening, sealed material, that a sealed material adds 2 more surface resistance. So, a sealed adds 2 more surface resistances and 1 more space resistance. In fact, if you see the electrical analogous diagram, so this is the electrical analogous diagram. If we say that this, so this is say EB1, this 1 by A1 F12, this is J1, I am sorry, this is 1 minus epsilon 1 by A1 epsilon 1, this is J1 is 1 by A1 F12, and this is then J2, and this is 1 minus epsilon 2 by A2 epsilon 2. So, this is for without radiation shield. This is the electrical analogous diagram. Now, when there is a radiation shield, then what is happening? This becoming more. There will be 3 more resistances are added. So, there will be 3 plus 3 6 resistances. So, if I write over here, so EB1, then it is J1, then it is becoming J3, then it is becoming say EB3, okay. Then it is becoming okay. So, J3 dashed, then it is becoming EB2 and sorry J2, and then it is becoming EB2. This is what is becoming. So, we have 1, 2, 3, 4, 5, 6 resistances, and 3 resistances. Initially it was, now 3 resistances have been increased. Among the 3 resistances, what we can understand, these 2 are the surface resistances. This is 1 minus epsilon 3 by A3 epsilon 3, we can say, and this is 1 minus epsilon 3 by A3 epsilon 3. Now, this I will say epsilon 3 dashed, it may change. The shield may have one side one emissivity, another side it can be another emissivity, but in general epsilon 3 is equal to epsilon 3 dashed if same material. Okay. And then other things are understood, that 1 minus epsilon 1, sorry, if I write 1 minus epsilon 1 by A1 epsilon 1, this is 1 by A1 F12, I am sorry, it is F13 now, and then this is the space resistance, this is another space resistance, this is again sorry, this surface resistance, this is another surface resistance for 2 sides, Now, it is becoming another aspiration. This is A3 F32 or and then it is 1 minus epsilon 2 by A2 epsilon 2. This is the surface radiations for this second one, and this is the surface radiation for the first one, and these two are the surface radiations for the radiational sealed material. Okay. Now, we know that, so that part is for with radiation sealed. Okay. Now, what we can understand that rate of heat transport, rate of radiation energy transport, okay, without the case of sealed. Okay. In that case, we have that q dot by A is equal to sigma into T 1 to the power 4 minus T 2 to the power 4 by all the resistances. Okay. And the resistances are 1 minus epsilon 1 A 1 epsilon 1 plus 1 by A 1 F 1 2 plus 1 minus epsilon 2 by A 2 epsilon 2. Okay. Now, let us assume large plates, okay, and epsilon 1 is equal to epsilon 2 is equal to epsilon 3, that is for sealed material. So, large plates means A 1 is equal to A 2, and for large plate, so the areas are same, and F 1 2 is equal to 1. So, it that first plate see only second plate, it does not see anything else. So, view factor is equal to 1, and then it becomes sigma into T 1 to the power 4 minus T 2 to the power 4 by, if we just do the simplifications, we get here it is q dot is that. So, you can write A 1 is equal to A 2 and that is equal to say A. So, q dot by A, that becomes 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, this becomes the case, it is a simplified form. Now, with, so for case with sealed, and then rate of radiation heat transport between surface 1, say between plate 1 and the sealed, that is equal to say q dot by A, using the similar kind of things 1 to 3 basically, and that will be equal to sigma into T 1 to the power 4 minus T 3 to the power 4 by 1 by epsilon 1 plus 1 by epsilon 3 minus 1, and that will be equal to sigma into T 1 to the power 4 minus T 3 to the power 4 by 2 by epsilon minus 1. In fact, in the previous case also, this will be equal to sigma into T 1 to the power 4 minus T 2 to the power 4 by 2 by epsilon minus 1 when epsilon 1 is equal to epsilon 2. Similarly, here when epsilon 1 is equal to epsilon 3. Similarly, then rate of radiation heat transfer between the sealed and plate 2, that will be q dot by A, and that is 3 to 2. Okay. That will be equal to sigma T 3 to the power 4 minus T 2 to the power 4 divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay. And that is becoming sigma into T 3 to the power 4 minus T 2 to the power 4 by 2 by epsilon minus 1. So, here again that epsilon 2 is equal to epsilon 3, that assumption is being taken. So, under this situation, so at steady state, say q dot, q dot by a from 1 to 3 will be equal to q dot by a from 3 to 2. That means, that is, it gives us that T 3 to the power 4 is equal to half of T 1 to the power 4 plus T 2 to the power 4. Okay. And then, then we can write the heat transfer rate q dot by A equals to half of sigma into T 1 to the power 4 minus T 2 to the power 4 by say 2 by epsilon minus 1. So, what we can say is that heat flow rate, just by putting the shield, heat flow rate is just 1/2 of that which would be experienced if there were no shield present. So, that means, so we just wanted to see that when there is a between two plates, if we put a single shield, then the heat transfer rate is becoming half. It is it's becoming it's reduced and it's becoming half of that original case it would have been. But this derivation had a lot of assumptions had been taken, all the emissivities are same, these are two large plates and their view factors are 1 and all these assumptions are being taken. Now, does it mean that putting the shields we are reducing this into just 50%? It is the case of just for a single shield. Now, if we put n number of shields, then the situation becomes a different things. So, for n shield in the present situation, so situation would be different for different cases, because in this present situation means there are a lot of assumptions are being taken. Assumptions are that the large plates, they have again the view factors are 1 and their areas are same, their emissivities are also same, all these things has been taken into consideration. And now, in this case, when there are n shield present, then total resistance will be 2n plus 2 n into 1 minus epsilon by epsilon. This will be the surface resistance, plus there will be n as n shield. So, 2 n surface resistances for these, and for the two other plates, for the two plates there are 2 surface resistances. So, total surface resistance will be 2 n plus 2 and these the area is same, and plus n plus 1 into 1. This is the another resistance. This resistance is due to view factor resistance, okay, per unit area. This is the per unit area. So, then what happens is, we know that this total resistance into by A, if we put it that 1 by n plus into 1 by A 1, 1 by A F 1 2, F 1 2 is equal to 1. Okay. So, this is A, this is the total resistances. Now, when no shield is present, the resistance is just 2 by epsilon minus 1, that is what. And so, this is 2 by epsilon A my 1 by A. So, we can say that okay, this is again 1 minus epsilon by epsilon A plus 1 minus epsilon by epsilon A plus 1 by A, and that is equal to 1 by epsilon A into 2. So, 2 by epsilon A plus 2 by A minus 2 by A plus 1 by A. So, it is becoming 2 by epsilon A minus 1 by A. So, this is the resistance. Now, if I just see that flux, so per unit area, so resistance unit area, if I considering the area, then what we will get is, or so Q dot by A, if you try to find out that with shield, okay, will be equal to 1 by n plus 1 times Q dot by A without. How we are saying that? If you see here, this part, the total resistance part, this can be written as this is equal to n plus 1 into say 2 by, again the same thing will come, epsilon A minus 1 by A. That is what is going to come. So, this is anyway, it is just n plus 1th time. The total resistance is n plus 1th time more than the original resistance. So, it is not every time we will just get 50%. So, for n number of cells, it is just that rate will be reduced by n plus 1th times. That means, we got half because we had 1 cell. So, 1 plus 1, that is 1 by 2. Okay. So, this is what is the case, that change in without shield, whatever heat transfer is there will be, with shield will be getting 1 plus 1 by 1 plus nth times the heat transfer will be getting. So, that will be reducing the heat exchange. So, this is the role of a radiational shield, that is what we can understand. Now, next part what we are going to discuss is this gas radiation. Now, in case of gas radiation, it is very important that we have discussed as of now that radiational heat exchange between different plates, different surfaces. But in between the surfaces there are certain gas, there is a certain environment, that is the air or maybe some other gases being present. So, what is their role in this radiational heat transport? Actually, they have a significant role, but not all the gas elements. For example, in case of air, if you consider there are nitrogen, oxygen which are present. This nitrogen, oxygen, they are assumed to be, or they are likely to be say transparent. These are called transparent gases. They do not absorb anything, any radiation, and so that's not a problem. The problem associated with the higher molecular weight gases, and typically carbon dioxide, water vapor, okay, then hydrocarbons, CFCs, chlorofluorocarbons. So, these are the gaseous substances or the vapors, ammonia. Okay. So, these are the ammonia vapors. So, these are the gaseous substances or ammonia, I am sorry, ammonia gas. These are the gaseous substances which do participate in absorbing certain radiation. That means, some of the wavelengths are being absorbed by these gaseous substances, and thereby they do affect the radiational heat exchange performances. Radiational heat transfer performances are being affected, are being influenced by the absorption and emissive power of these particular gases or the vapors. And we know that these are the gases or the vapors, because of those reasons they are responsible for global warming, and carbon dioxide is called a greenhouse gas, that we always know. And what happens is, it is assumed that when sun rays are coming, sun radiations are coming, mostly that all these, it is a high frequency radiations, these are coming and they are not being absorbed while it is coming by that, and they are easily penetrating into the atmosphere of earth, and then it is striking the earth surface, and while it is the earth surface is radiating that energy, then it is that longer wavelengths are being absorbed by this carbon dioxide and these other HFCs, CFCs and hydrocarbons, and thereby they are trapping the energy in the earth and then increasing the temperature of the earth, and therefore the global warming takes place. So this is about that history of global warming, and therefore it is also related to the gaseous absorption and emission of the gases of the radiational energy, and therefore it is very important, and we should have some idea about that how does it work. Now what we will do is that to understand these phenomena of absorption by the gases, we will develop an expression to see that what is that absorptivity of gas is. Now consider a gas layer, and which is having a say differential thickness is this. So this is a dx, and this is the layer in x direction, and this part is say x at a distance x, and this is the x direction. So some radiation is coming here, and which is at I lambda 0. So it's a monochromatic radiational intensity which is coming at x equal to 0 is this, and which is coming at x equal to x is I lambda x, okay, and this is the dx, and this is x equal to 0, and this is x equal to L. So we are considering say a gas beam of length L, okay, and say I lambda is the monochromatic, it is also called spectral radiation intensity falling on the gas beam. Okay. So now at a distance falling on at gas beam, so I lambda x is at x is equal to x. So this is the radiational intensity that is falling on the gas beam. Now what we can say, because of this gas, if it absorbs the radiation, there will be a decreasing in the intensity of the radiation, and therefore the decrease in intensity of radiation would be due to absorption in gas layers, okay, and this is decrease is proportional, the decrease is proportional to the thickness of the layer. So that means after passing through a small layer of differential thickness say dx, the intensity is decreased by to some extent, okay, layer, and the intensity of radiation at that point. So if the decrease in intensity is d I lambda, so minus d I lambda, means it is a decrease is proportional to I lambda in, and it is also proportional to dx. So we can write that d I lambda equals to alpha a lambda I lambda dx, where a lambda is a specific terminology. It's a proportionality constant, but it has got a significance, proportionality constant, but it is called as monochromatic absorption coefficient, monochromatic, or it is also called spectral also it is called monochromatic extinction coefficient. Okay. Then after integration, this is here minus. So after integration, d I lambda by I lambda and so I lambda at a point, this should be x, this should be x. Okay, d I lambda x, and this is I lambda x. So I lambda x is important, d I lambda x, and this is 0 to I lambda x, and that should be equal to minus a lambda. Assume that a lambda does not change with x, integral of 0 to x dx. So this says that I lambda. So from here we can write that I lambda x by I lambda 0, that means this is I lambda 0, okay. X equal to 0, it is lambda initial intensity will be equal to e to the power minus a lambda into x, okay. So here a lambda is not function of x, that is being assumed, and this is called Beer's law. So Beer's law says basically that how the intensity is being changed when a gas beam do absorb radiation. Now this also can be written as I lambda x by I lambda 0, also can be called as tau transmittivity. So this is say tau lambda, it is called monochromatic transmittivity. So then tau lambda, we can write tau lambda is equal to e to the power minus a lambda x. Again we know that alpha lambda plus tau lambda plus rho lambda will be equal to 1, but in this case we will assume this is equal to 0, that means there is no reflection, okay. So reflectivity is equal to 0 for the gaseous. Then what we can write as alpha lambda is equal to 1 minus tau lambda, that we know. So then we can write that alpha lambda is equal to 1 minus e to the power minus a lambda into x. So this says that this is nothing but the monochromatic emissivity, absorptivity, and this also can be written as epsilon lambda if Kirchhoff's law hold good, okay. So this is also called that monochromatic emissivity, and this is monochromatic absorptivity. Now this x is called the length. Now when we have the length of the beam, so for when it is x equal to L, then it will be L. So therefore this x is, or the length of the beam is very important, because the gas absorption, gases absorb absorption of radiation by gases takes place for a narrow band of emission spectrum, okay, or narrow band of wavelength, whatever you say. And this it is dependent on partial pressure of gas, then temperature and path length, that is very important, path length traversed by the radiation through the gas. Now this path length traversed by the radiation, that can be, that is a very significantly, it can vary from considerations to considerations. So this path length varies over the range as radiation incident on a surface moves at all possible angles through the gas. So, therefore, the path length can vary. So, normally there are some path lengths are being told for standard geometry, some mean beam length is known. For example, say long cylinder, characteristic dimension, and this mean beam length. I will say this in the, we will make a table for that. For example, it is like this, that shape of geometry and then characteristic dimension and then here the mean beam length LE. And here for long cylinder, so diameter D and here it is 0.94 D. For sphere, it is a D diameter and this is 0.63 D. For cylinder, say for cube, and radiation to all surfaces, say it is so length of a side say L and this will be 0.66 L. Similarly, infinite parallel plates separation distance say S, this will be 1.80 S. So, like that for different geometries in the literature or in different books, the values of mean beam length is being there. However, for non regular geometry an approximate estimate of mean beam length is L equal to 3.6 V by A, where V equals to volume and A equals to area of the enclosure. So, basically when we have an enclosure and in the enclosure there is a gaseous medium, so this how to what extent how much thickness of the gaseous medium that radiation is passing through, that is very important, which is nothing but is given by the mean beam length, so that some reasonable estimate can be obtained for these cases. Now, if we try to concentrate on the part of heat exchange, between gas volume and black enclosure, we will see that Q dot by A net will be energy emitted, that is the flux emitted by gas minus energy from the enclosure absorbed by gas. So, this is actually you can write epsilon g, which is a function of T g. T g is the gas temperature, gas at temperature T g and enclosure at temperature T w. So, epsilon g sigma T g to the power 4 minus alpha w, alpha is the absorptivity of the gas, alpha g, and that will be at T w and sigma T w to the power 4. So, T w is the wall temperature. Okay. So, epsilon g is the gas emissivity at T g and alpha g is the gas absorptivity at T w. Okay. Now, emissivity epsilon g is calculated as summation of C I epsilon I minus delta epsilon. Now, what is this? This epsilon g is the emissivity of the gas mixture. Okay. So, the gas mixtures can have different gases can be having different emissivities. So, this is what is being given, and delta epsilon is the correction for the mixture. That means, it is the individual emissivities minus the corrected emissivity, and then with the individual emissivity there is a correction term. This correction term C I is a correction for total pressure greater than 1 atmosphere, and epsilon I is the individual component emissivity. Okay. Now, in case of air as the gas, we have mainly CO2 and water vapor as the important gases. The other gas, oxygen, nitrogen, they do not participate in these particular things, radiation part. So, therefore, then epsilon g will be C C for carbon dioxide, epsilon C plus C W epsilon W minus delta E. So, this C C and is equal to C W is equal to 1 when total pressure P T is less than equal to 1 atmosphere. Okay. Then this correction is not needed, fine. And similarly, so we can find out this epsilon g like that way. So, if I see that our expression says there is a necessity of getting these values of epsilon g, and the epsilon for different at different temperature and pressure conditions for different substances can be obtained from the figures. So, from the figures in various books and references, epsilon I and C I values for various gases can be estimated. Okay. Now, I have to find out the alpha. Similarly, okay, alpha g is also calculated as summation of alpha I minus delta alpha. In the similar way, where for gas, for air, okay, alpha g at T w that is calculated alpha c plus alpha w minus delta alpha, and here alpha c is again C c epsilon c dashed into T g by T w to the power 0.65, and alpha w is equal to C w epsilon w dashed T g by T w to the power 0.45, and delta alpha is equal to delta epsilon at TW. So, from the figures again these can be calculated. Only thing is that epsilon C dash and epsilon rho dash are evaluated for PC LE TW by TG and PC PW LE TW by TG as parameters. And in the previous case, from the plots that epsilon C and epsilon W are calculated when and PC into LE and PW into LE are the parameters. Okay, so these plots are temperature versus epsilon, and there are different values for the parameter Pi into Le. This is the parameter. Okay, so for this parameter, but in the case of here the dashed means the parameter is changed. That means it is corrected with respect to TW, because we are considering the case of TW is the corrected with respect to therefore TW. So, therefore, the parameter is changed. Now, one thing is there that hotel has recommended that the net heat transfer to a gray enclosure with emissivity epsilon g is given as q dot gray by q dot black equal to epsilon g plus 1 by 2 for epsilon g is greater than 0.8. That means, for higher values for gray, we have seen that for the black enclosure. Now, if we have a gray enclosure, then we can calculate for black enclosure, and then from there we can calculate for gray enclosure, provided that epsilon g is greater than 0.8. If epsilon g is less than 0.8, then rigorous calculation is needed, and which is beyond our discussions in this particular lecture hours. Okay. Now, I will take up a few problems to discuss on this. First one is problem 1. Say a gas at 300 Kelvin present in a test cell of length 12 centimeter is found to absorb 88% okay, of incident monochromatic radiation at lambda is equal to 4.0 micrometer. Okay. So, what is the value of say A lambda? So, now we know solution I tau lambda is equal to exponential minus A lambda into L. Okay, that is what already we have seen, and L is equal to 0.12 meter. So, that integration if we just do from 0 to L, x equal to L, then we will get this expression. Okay. And tau lambda is equal to I lambda L by I lambda 0, and that is equal to 0.12. Okay. Just we will put these values over here, then we will get A lambda is equal to 17.67 meter inverse. Now, second problem we will discuss is that on radiation shield. Quickly we will say that a tube with OD outside diameter 2.54 centimeter transports a liquid at minus 190 degree centigrade. The tube is enclosed in an evacuated concentric pipe of ID inner diameter equal to 5.0 centimeter with wall temperature of 0 degree centigrade. A thin walled radiation shield is placed midway in the annulus. Okay. Now, calculate the heat transfer rate. Okay. Given emissivity data, so tube wall 0.06, pipe wall 0.12 and sealed material 0.02. Now, if we have to solve this problem, it is understandable that it is like that there are some concentric pipes. So, in this pipe and we are putting some sealed material here. It is not exactly what is being we have discussed in case of large parallel plates, shielding for large parallel plates. Here it is the area is different for different cases. So, that is has to be that is the main point of consideration. So, if we say that I indicates inner tube, O indicates outer pipe, then S indicates radiation shield, then for net radiation rate of heat transfer from outer pipe to inner shield, Q dot O S outer pipe to inner shield is equal to A naught sigma T naught to the power 4 minus T s to the power 4 by 1 minus epsilon naught plus 1 by F naught S. So, this is the view factor plus A naught by A S into 1 minus epsilon naught by epsilon S by epsilon S. The important thing over here is that view factor has to be calculated also in this case it is not 1, and similarly now net rate of heat transfer from shield to inner tube, that is Q dot S I, that is again A S sigma T s to the power 4 minus T I to the power 4 divided by 1 minus epsilon S by epsilon S plus 1 by F S I plus A S by A I into 1 minus epsilon I by epsilon I. I indicates the inner tube. Now, the data given DO is equal to 0.05 meter, DI is equal to 0.0254 meter, then DS is equal to DO plus DI by 2 and that is 0.0377 meter. Then the length is equal to 1 meter. So, area for AO outer pipe area is equal to pi dl for all the cases pi do into L, and that is equal to 0.157 meter square. Similarly, AS will be equal to pi dl again 0.118 meter square, and AI will be equal to 0.0798 meter square. In the similar way, if we do, and then given is epsilon 0 is equal to 0.12, epsilon is equal to 0.02, and epsilon I is equal to 0.06, and T naught is equal to 273 Kelvin, and T I is equal to minus 190 plus 273 is equal to 83 Kelvin. Then we know that FSO is equal to 1. That means the sealed, if we just see here, F is equal to 1 means that this is the sealed material, this outside is the convex. So, this is equal to 1. Okay. Similarly, this I also will be equal to 1, IS will also be equal to 1. So, based on that, FSO equal to 1, then FOS is equal to AS FSO by AO, and that is equal to 0.118 into 1 by 0.157, and that is equal to 0.75. Then we know AI FIS equal to 1, as I told, FIS is equal to 1, and then from there I can get FSI is equal to AI FIS by AS, and that is equal to 0.798 into 1 by 0.118, and that is equal to 0.676. So, now we can find out that capital R1, that is equal to 1 minus epsilon 0 by epsilon 0 plus 1 by FOS plus A naught by AS into 1 minus epsilon s by epsilon s. Putting all the values, this comes to be 73.85. Then capital R2 is equal to 1 minus epsilon s by epsilon s plus 1 by FSI plus AS by AI into 1 minus epsilon I by epsilon I, and that is equal to 73.30. So, once we know these values, then putting those there, we can get that 0.157 by 73.85 into TO to the power 4 minus TS to the power 4 is equal to 0.114 by 73.30 into TS to the power 4 minus TI to the power 4, and from here we can guess, TS we know it is 273 to the power 4, and this is TI is equal to 83 to the power 4. From here we can get our TS as 238.4 Kelvin, and Q dot is equal to 0.157 into 5.669 into 10 to the power minus 8 into 273 to the power 4 minus 238.4 to the power 4 to the power 4 divided by 73.85, and this value is equal to 0.28 watt. So, this is the rate of heat transported from the outer pipe, to inner one, to the inner pipe at steady state. So, rate of this is to sealed, and that has to be to the inner pipe also at steady state. So, this is all about that radiation exchange. I have shown that how to calculate for putting a sealed in case of cylindrical coordinate system also. So, to summarize that we have discussed in the radiation heat exchange, we have discussed in the radiation heat transfer, we have discussed that various introductory concepts, and then we have discussed some various laws, and then we have seen that how to find out the radiation safe factor, and then we have seen that how to calculate that radiation heat exchange, and then application of sealed and how to get the values of heat exchange when there is a sealed, and we have demonstrated through problems that how this is can be evaluated. So, some more and more problems can be tried upon, so that it will be easy for people to understand. Thank you very much.